Have you ever stopped to wonder what the literal, absolute physical limit of human engineering actually looks like? Seriously, think about it. It's not some massive rocket ship, right? And it's not a mile-high skyscraper. It is a machine that operates so close to the edge of physics, it almost feels like magic. And it happens to be the single defining bottleneck for the entire future of artificial intelligence. Welcome to this explainer. Okay, we've got a lot of ground to cover because today we are tearing apart the mystery of the most important company you might have never fully understood, ASML. We're going to dive deep into the impossible tech that literally makes our modern world tick.
The most technically advanced tool of any kind that's ever been made. Just let that sink in for a second. The most advanced tool of any kind. Every single AI query you run, every mindless swipe on your phone, every video you stream, it all traces back to one very specific type of machine. If this technology suddenly halts, the entire digital world grinds to a dead stop. So yeah, the stakes for human progress literally do not get any higher than this.
Boom. $400 million. That is the jaw-dropping price tag for just one single ASML high-NA extreme ultraviolet or EUV lithography machine. $400 million. That's twice the cost of their previous generation, which officially makes it the single most expensive piece of manufacturing equipment in human history. And when you peer inside one of these absolute behemoths, you immediately see why. This astonishing internal complexity is exactly what buys you the future of AI. It prints chip features in a single pass that used to require 4 incredibly error-prone steps. It's essentially laying out incredibly complex transistor patterns onto silicon wafers, where each individual line is literally thousands of times thinner than a single human hair.
Okay, to even wrap our heads around the logistics of this machine, let's just rattle off some insane stats here. One of these units weighs 200 tons. 200! It contains over 100,000 precision parts, 3,000 cables, and 40,000 bolts. And getting it to a customer? Oh, you don't just put this thing on an 18-wheeler. It requires 40 shipping containers spread out across 3 separate cargo planes, just for one single unit.
Section 1. The world's most important machine. So, exactly why does this machine defy belief? Section 2. Creating the impossible light. To really understand its importance, we have to look at the mind-bending, action movie-level physics required to make modern microchips by creating something known as impossible light.
All right, let's start with a quick baseline. Traditional photolithography is, well, it's basically a high-tech stencil. Light is filtered through a mask that contains a circuit pattern, beamed through a lens, and projected onto a silicon wafer covered in light-sensitive chemicals, kind of like developing an old-school photograph. But to make the chips needed for AI, the features need to be way smaller than what normal light can physically draw. We need extreme ultraviolet light.
But here's the catch. Getting that extreme ultraviolet light is violently difficult. First, high-power CO2 lasers are fired. Then, these lasers have to perfectly target microscopic droplets of molten tin that are falling through a vacuum, blasting them 50,000 times every single second. This creates a microscopic plasma explosion hotter than the surface of the freaking sun. That fleeting little explosion is what generates the ethereal 13.5 nanometer EUV light, and it is incredibly energy intensive. Only about 3 to 5% of the laser energy actually gets converted into usable photons.
Now, because EUV light is absorbed by almost everything, and I mean everything, including regular glass lenses, ASML has to use incredibly precise mirrors to guide it. And these aren't just any mirrors. These are multi-layer mirrors made by Zeiss, built to absolute atomic precision. To grasp just how flawless they are, think about this. If you scaled one of these mirrors up to the size of Germany, the biggest imperfection on its surface would be smaller than a single millimeter. No way, right? But that is the exact level of precision required to bend this impossible light.
Section 3. How ASML became a monopoly. So how on earth did a company you rarely even hear about manage to totally monopolize the most advanced manufacturing process in human history? Well, it's a classic David versus Goliath story.
Knowing about the $400 million machines they make today, it is honestly hard to believe their origins. Back in 1984, ASML started as ASM Lithography. This little struggling joint venture spun out of the Dutch electronics giant Philips. They were quite literally relegated to leaky sheds just outside Philips' headquarters in Eindhoven. They started with exactly 47 reluctant employees and 17 prototypes. In fact, many of those employees demanded a written guarantee that they could return to Philips if this super risky startup went under.
But then came a massive market share flip.
In 2001, Japanese giants Nikon and Canon totally dominated the lithography space. ASML was a distant third at just 22.4%. But ASML decided to make massive, high-risk bets on next-generation tech, while Nikon and Canon kind of hesitated or chased dead-end technologies. By 2011, ASML had utterly crushed the giants, capturing 57% of the market, while Canon and Nikon just bled share.
And that insane trajectory led to a staggering outcome. Today, ASML's global market share in extreme ultraviolet lithography is exactly 100%. 100%. They are a total absolute monopoly. Canon and Nikon are now stuck producing legacy equipment. They misjudged the technological transitions years ago and face a gap they simply cannot close.
Section 4. Hidden challenges in production. Because as it turns out, actually operating these machines is an absolute nightmare for engineers.
Yeah, this is definitely not plug-and-play technology. The components inside operate at the very edge of material limits. Those laser mirrors, they literally erode away in 1,200 hours. The nozzles blasting that molten tin clog up weekly. Vacuum bearings have to be replaced every single year. Protective films called pellicles cost 10 grand a pop and are incredibly fragile, deforming under the 500-degree heat. And get this, if there is a single invisible defect buried in a mask, it will print flawlessly, effectively ruining thousands of chips before anyone even notices.
Oh, and the biggest catch of the whole shebang? UV light is absorbed by air. So this entire violent, explosive process has to happen inside an absolute extreme vacuum. And to stop tin debris from ruining those pristine Zeiss mirrors, fabs have to inject highly pure, highly flammable hydrogen gas into the chamber to clean them chemically. So you're mixing high-power lasers, molten metal, and explosive gas inside a vacuum. It is an operational tightrope like nothing else.
Section 5. The future of artificial intelligence. Now, why should you care about all this intense engineering stress? Because the entire future of artificial intelligence completely relies on this one global choke point.
Right now, a massive strategic divide is tearing the semiconductor industry apart. Intel is basically betting the entire company on these new $400 million high-NA machines. They are ASML's first customer for them, planning volume production by 2027 to try and regain their manufacturing crown. But TSMC, the current undisputed king of making chips for Apple and NVIDIA, is actually sitting this generation out. They claim they can squeeze more life out of their older EUV machines by just running the wafers through multiple times. The entire chip roadmap for the cloud providers powering your favorite AI tools completely depends on who wins this multi-billion-dollar gamble.
So everyone wants to know, when will AI chips actually become cheaper and more available? Well, let's look at the timeline. In 2025, AI chip shortages were driving memory prices up over 50%, causing massive project delays across the board. And even with ASML hitting production milestones today, Intel won't ramp up real volume until 2027 or 2028. It actually won't be until 2030, when ASML projects throughput hits 330 wafers per hour, that global supply truly stabilizes. So the cavalry's coming, but guys, they are still years away. And if you're wondering, hey, can't someone else just swoop in and build these machines faster? The short answer is no, they can't. ASML has an unbreakable moat built entirely on optics. They essentially operate as two companies, one business, with Zeiss. Decades of co-development and an exclusive partnership mean absolutely nobody else has access to the subatomic mirror polishing required. Not Canon, not Nikon, not even heavily funded efforts in China. The physics and supply chain integration is practically an insurmountable barrier.
Which leaves us with this final, truly provocative thought. We spend all our time debating code, right? Algorithms, neural networks, data sets. But as we've seen today, the true bottleneck of the AI revolution isn't the software at all. I really want you to ask yourself, will the ultimate limits of AI be determined by human ingenuity and software, or by the brutal, unyielding laws of physics inside an ASML machine? Thanks so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you in the next one.